Hello viewers, Wagadaruna taking you through the story for A-Level Physics Paper 2. And this video I'm going to go through the entire calculations in electrostatics. So this video is suitable for students in both Senior 5 and Senior 6 offering physics as part of their combination. So before we proceed, let's first look at the course outline for A-Level Physics Paper 2. So A-Level Physics is divided into four parts. The first part is geometrical optics, where 2 questions come from these topics, and a student must answer one. Next part is physical optics or waves, where 2 questions come from these topics, and a student must answer one. The next part is electrostatics and electricity, where 3 questions come, and also magnetism and AC, where 3 questions come from these topics. So it is up to the student to choose. If you choose 2 questions here, you will choose one here, or if you choose 1 question here, you must choose 2 questions here to make the 5 questions which are needed. So in this video, I'm going to go through the calculations for electrostatics. Now those calculations are broken down into 5 parts. The first part is called Coulomb's law, where we look at electrostatic force. Then next part is electric field intensity at a point. Then electric potential at a point. Then electric field intensity between 2 parallel plates. And lastly, closest distance of approach of an alpha particle to the nucleus. So all these parts will be catered for in this video. So we are dealing with calculations, but if you want notes and trial questions, they can be found in this book. So this book contains notes, worked examples, and trial questions for all the parts of Physics Part 2. But our emphasis on this YouTube channel will be the part of worked examples which are found in this book. So if you need the copy of this book, you can contact the author on any of those 2 lines. So now let's start with our topic of Coulomb's law. So Coulomb's law states that the force between 2 point charges, Q1 and Q2, so Q1 and Q2 are the point charges, is directly proportional. So this word directly has to be seen. Most students want to write only the word proportional, which is not okay. So directly proportional to the product of the magnitude. So even this word magnitude is needed because the charge can be positive or negative. But what we mean by magnitude is that what is negative becomes positive. So when you are calculating, you ignore the negative and you write only the positive. So the magnitude of the charges, and inversely proportional to the square of their distance of separation r. So r is the distance of separation. And if you want to write it mathematically, it will be in this form, that F, where F is the force, Q1 and Q2 are the point charges. They say it's a product, that's why there is this multiplication. Then inversely proportional means inversely is the reciprocal, so that's why there is this r squared, because they said square of the distance of separation r. Now, if I want to remove this in proportional sign, I have to put a constant of proportionality. So in this case, let us use k. But in physics, that k has a value. So the value is 1 over 4 pi epsilon. So this symbol is called epsilon. And that epsilon represents the permittivity of the medium in which the 2 point charges are located. So medium can be air or any other insulation. So most cases we usually use air or free space. So that means that when you substitute for k, this k, when you put it here, we are going to come up with this expression. But like I said, we usually use free space as the medium. So when you use free space as a medium, remember to put this note, epsilon naught. Now this epsilon naught means permittivity of free space. So in this case, the medium is free space. And that constant has a value which is 8.85 exponent negative 2 farad per meter. Now these constants, you don't need to cram them. They will be given to you in a paper. The first page always has the table of constants. Now because you have the value for permittivity of free space, you can come and substitute it here to get the value of this constant of proportionality k. So when I substitute it here and I use a calculator, I'll come up with a value which is this 9 exponent 9 meter per farad. Remember, this one alone was farad per meter, so the reciprocal becomes meter per farad. So it's okay to use this, but it is easier if you use this very value instead of epsilon naught. So in that case, it means that when I'm calculating for force, it is better if I use this value, so that where there is k, I put there 9 exponent 9. However, it is also okay if you use this expression and you substitute 8.85 exponent negative 12. But I would prefer this, and in this video we shall be using this expression where I just substitute directly for the constant of proportionality. So that means that in free space, F is equal to K Q1 Q2 over R squared, where K is equal to 9 exponent 9 as we have got it here. So this expression is also given in the table of constants. There's no need to memorize it. It is available in your table of constants. They don't write it as K, they write it as 1 over 4 pi epsilon naught. So you need to know that 1 over 4 pi epsilon naught is the value of K. So now that we have seen how to calculate the force, we need to know the law of electrostatics. So it says that like charges repel each other while unlike charges attract each other. Why do we need to know this law? It is because force is a vector quantity. Therefore, we need to know, when we are taught to calculate force, we need to write magnitude and direction. So a vector quantity always has magnitude and direction. So this expression gives you the magnitude of that force, but you also need to specify the direction of that force. So now, because you need to specify the direction, that is where this law of electrostatics comes in, whereby we need to know that like charges repel. Like charges means both are positive or both are negative, and unlike charges attract. That means one is positive, the other is negative. I think let us first illustrate this. So if I have two metal spheres and I fix them, so this one shows that I'm holding them fixed at that position so they don't move. Then I apply a charge, positive charge here and a positive charge here. Now because there is a positive, both charges are positive, there will be repulsion, just as you can see it here. So one will, if we didn't hold this one fixed and this one fixed, then this charge would go this side and this charge will also go this side. But both are fixed, so there's only repulsion. So the one holding them will feel the repulsion. So this will be the force on Q1 due to charge on Q2. So this charge applies a force on this charge, and also this Q1 applies a force on Q2. So that will be force on Q2 due to charge at Q1. Now these forces are in opposite directions, but they have the same magnitude. So we shall say that F12 is equal to F21 and is given by the formula K21 over R squared, which we have already seen. Now it will be the same case if both charges were negative. So this is a negative charge, this is a negative charge, so there will be repulsion. That's why the directions will remain the same. But what you should realize is that though this is negative, here we have written positive Q1. And though this is negative, here we have written positive Q1. Why? Because we said in the law, Coulomb's law, that magnitude of charges, so you only get the magnitude. Magnitude means what is negative becomes positive. What is negative becomes positive. So always remember that this is used to get the magnitude. Then after getting the magnitude, you have to use the law of electrostatics to get the direction. Now what if the charges were of opposite signs? So we have two metal spheres, we fix them and we give one a positive charge and the other a negative charge. So in that case there will be attraction. So the direction changes. Here for repulsion, one was going this side, another on this side, but for attraction they are pulled towards each other. So still this will be the force on Q1 due to charge on Q2, and this will be the force on Q2 due to charge on Q1, and the magnitude will be the same for both forces. And it is the same as before. That is if the separation is the same and the magnitude of the charges is the same. So it's the same if we interchange the charges. This is negative. Previously it was positive, negative. Now it is negative, positive. Still there will be attraction, and the magnitude of the force will be the same. So with that, we shall go through some of the questions. Question 1 came from UNEB 2012, paper 2, question 9C, and says the figure below shows the charges Q1, Q2, and Q3 of positive of this, and that, respectively, placed in a straight line in air. So air is the same as free space, just as you can see them here. Then they said find the force on Q3. So they want you to find the force on this Q3. So there will be a force on Q3 due to charge Q1, and also there will be a force on Q3 due to charge Q2. So I'll start with one of them. So here I can say, let me start with the force on Q3 due to charge Q1. So in that case, the separation will be 20 plus 10, which is 30 centimeters. And also you realize that both are positive. Now because both are positive, here there will be repulsion, so it will go to the right. Therefore I'll come here and say that the force on Q3 due to charge Q1 is given by that formula. Then I substitute for K, substitute for Q3, substitute for Q1, and then substitute for the separation. So now separation will be 30 centimeters, but I convert it to meters to give you 0.3. Also, the charge was in microcoulomb, but I have to change it to coulomb. That's why I multiplied by 10 to the power negative 6. So here it is advisable to, not advisable, but we have to change to SI unit. So when I use a calculator, I'll come up with this value. So I think we realize that I'm giving the magnitude and I'm also giving the direction. Why? Because force is a vector quantity. Then next I'll go to force on Q3 due to charge Q2. So if you go back to our diagram, there is this. So this is Q3 and there will be a force due to charge Q2. So in this case, the separation is 10 centimeters, which is 0.1 meter. And also realize that these are opposite charges, meaning there will be attraction. Therefore, this one will go in this direction. The force will act in that direction, which is to the left. So shall come here and write that force on Q3 due to charge Q2 is K, which is there, Q3 there, Q2 which is there, and separation which is that squared. But realize that I'm not putting a negative because we are interested in the magnitude for the calculation. Then we use the law of electrostatics to get the direction. So when I use the calculator, I'll come up with this, and then I have to give the direction to the left as we have seen in the question. So now I have one force to the right, and another force to the left. And what they want is the resultant force. So this force to the right is bigger than the force to the left is bigger than the force to the right, meaning that the resultant force will be to the left. Therefore, I'll come and say that I'll take the force to the left to be positive and the force to the right to be negative, and I'll come up with this magnitude to the left. So we're putting in this minus because they are in opposite directions. This one is to the left and this one is to the right. But for you to know which one to put first, you look at the one which is bigger, so in magnitude. So this one is bigger in magnitude to this, meaning that I'll first put this one here and subtract off this. Then the direction will depend on the one which is bigger. So this is to the left. That is why I also write here to the left. So that was question 1. Now we shall go to question 2, which came from UNEB 2005, paper 2, question 10, D Roman 1, and says 2-point charges P and S. There is this P and there is this S. Of this and this respectively are placed in a vacuum. So vacuum is the same as free space. So they can use any of the three words. They can use air, they can use free space, they can use vacuum. At a distance of 21 centimeters, as you can see it there, apart. When a third charge, R, is placed midway between P and S, as shown above, the net force on S is 0. So when you put another charge here, previously the force on S was due to charge at P. But when you put another charge here, there will be also an additional force. So there will be also a force on S due to charge at R. So they say that in that case, the resultant will be 0. Then they say determine the charge on R. So in this case, we don't know the charge on R, but what we know is that the resultant charge force is 0. So how do we do such a question? So shall come and first get the force on S due to charge at P. So force on S due to charge at P, we shall have to substitute for K because it was vacuum, substitute for charge on S and also charge on P, and also the separation squared. So separation was 21 centimeters, but we have to convert to meters. That's why there is this 10 to the power negative 2. And also the charges were in microcoulomb. So usually the charges will always be in microcoulomb in most cases. So you have to remember to convert to coulomb. So now I substitute, I come up with this, and the direction is to the right. So why is it to the right? So we shall go back in the question and we find out why it is to the right. Remember, direction is got by using the law of electrostatics. So this charge at P is negative, and this charge at S is also negative. Now those are like charges, meaning there will be repulsion. So repulsion means that this charge is pushed to the right. Now it's also okay to put this one, but remember we are interested on only the force on S. That is why you are seeing me putting only this one, and I'm considering this direction. So that is how you get the direction of that force. Then next we'll go to the force on S due to charge at R. So force on S due to charge at R We shall come and also substitute for K, then for charge on S and charge on R, which we don't know, and the separation, which is this to meet in converted to meters. So we'll come up with this because this is unknown, so it has to be maintained. Now we are putting to the left. Now why are we putting to the left? We are putting to the left because they told us that the resultant force must be 0. So if this one is going this direction, one has to go in the opposite direction. So this one was to the right, meaning the second force must be to the left. Then from there, remember that for them to be 0, they should be equal and opposite. So resultant force will be 0. I'll come and substitute for resultant force, then this minus this. So that means that when I make true R the subject, I'll come up with this as my answer. And basically that's what they wanted. Then now shall go to question 3, which says that the charges this, and this, and that are placed at the edges of ABCD of a square as shown below. Find the resultant force on charge at C. So we have been dealing with the charges put in a straight line, but now this time the charges are put in a square. So how do we deal with such? So to easily answer such a question, you have to illustrate. So such questions, for a straight line, you don't need to illustrate. But when it comes to other shapes, they can be a triangle, square, rectangle. So for such shapes, you have to illustrate. So we shall redraw what is given. Then remember that the angle, because it's a square, this angle, which the diagonal makes with the horizontal, is 45 degrees. Then from there we shall start pushing the forces. We have start with force on C, because there is the force at C, the resultant force at C is due to these charges. Charge at D, charge at A, and charge at B. So the force at C due to charge at A, it will be this FCA. Now how do we know the direction? We use the law of electrostatics. Remember, this is negative, this is positive, meaning there will be attraction. That is why it is going this direction, because the force is attractive. Then the force on C due to charge at B. So first of all, this is positive, meaning there will be repulsion, so it has to go in this direction. Therefore, we shall come and show that direction. Then lastly, force on C due to charge at D. So this is positive, meaning there will be repulsion, so it goes in this direction. Therefore, we shall come and draw it. Like I said, we are only interested in the direction of force at that point which they want. For example, okay, let's say D and C, the repulsion will be represented by this force and also this force. But our interest is on the force at C. That is why we ignore this, and it is advisable not to indicate it anywhere. Only show what will help you calculate to get the required answer. So we only put the forces at C. So after that we have to calculate, but remember, when you're calculating force, you need separation. So this length is given, it is okay. This one is given, it is okay. This one is, but this one is not given. That is why you have to calculate for that this separation CA. Now separation CA is got by Pythagoras theory, this squared plus this squared, everything under square root, to give you this in centimeters. Then now that I've got the separation, I have to remember the formula, that it is K Q1 Q2 over R squared. Then I'll start answering the question. So force on C due to charge at A. Force on C due to charge at A. I'll come and substitute the charges. The K is this. One charge is this. That is charge at A, and this is a charge at C. Then this is the separation. So when I do that, the answer will be this. in newtons. What about force on C due to charge at B? So force on C due to charge at B, the charges are 3 and 8, but they are microcoulombs, so you have to convert to coulomb. Then the separation is 4 centimeters, which is converted to meters. Then use a calculator to come up with this. Now here, remember when it was a straight line, we used to we are showing magnitude and direction on the same line. But here, we are not showing the direction. Why? It is because we have shown this direction on the diagram. And that is the reason why I told you must redraw the diagram. As long as it's a shape of a rectangle, square, or triangle, you must redraw the diagram. So the directions are shown on the diagram, and here I only calculate the magnitude. So we have got force on C due to charge at B. Now we have to get force on C due to charge at D. So the charges are 5 and 3, and the separation is 4 centimeters. So shall come and say that force on C due to charge at D is given by that. K, charge of 5, charge of 3 converted to coulombs, or separation converted to meters, you come up with this. So we have got all the 3 forces. We have got this force, we have got this force, we have got this force. And the question is, how do we get the resultant? So resultant is got by resolving. I think you covered resolving and mechanics, that is physics paper 1. So we shall do this, we shall resolve, use the knowledge of resolving to get the resultant force. So when I resolve vertically, I'll come up with this minus this. So let's see how it comes about. So resolving horizontally, there is this FCD, which I have got in the next slide, minus, because this one now horizontally goes in this direction, because this one goes this direction and to the left and also downward. So to the left, it is this force which is here, and this angle is 45. So the horizontal component will be this cos 45. That is why in the resolving you saw this minus this cos 45, which is here, which is this 84, which is here, 3.375 minus this force cos 45 to give you that. Now we are not putting this other force because this one is entirely vertical, meaning its horizontal component will be 0. Now next we also have to resolve vertically. So resolving vertically, this one is going upwards, but this one, the component of this one is going downwards. So to be this minus this sine 45. Therefore, shall come here and write that resolving vertically, I'll come up with that, and I'll call it Fy. Now here we take horizontally, we take forces to the left as positive and forces to the right as negative. That is why there is this minus. Then vertically, we take forces upwards as positive and forces downwards as negative. That is why you see this negative there. So if we get a positive here, it means that horizontally it is to the left, to the right. And if we get a positive here, it means that vertically it is upwards. Therefore, when we are drawing our right angle triangle, we shall draw a positive horizontal, which is there, followed by a positive vertical. Then from there we shall join from start to end, and that will be your resultant. But remember, they want magnitude and direction, so we have to also go locate this, identify this angle. So we shall come and say, by Pythagoras theory, FC will be equal to this squared plus this squared and a square root to give you this. But we also need direction, so we shall say tan theta is equal to this over this to give you this as the angle. So angles are well expressed in two decimal places. The rest may be 4, but the angle should be 2. Then from there we shall come and conclude that the resultant force is this, which is this magnitude, in the direction this, above the positive horizontal. Now why do we say above positive horizontal? Now if we deal with this part is what we call positive part, and this part is what we call the negative part. Okay, then also this part is what we call above the horizontal, and this part is what we call below the horizontal. So if you look at this angle here, it is here. It is in this quadrant. So this quadrant, one, it is on the positive side of the x, and also it is above the horizontal. That is why we say above the positive horizontal. So now we shall go to question 4. It says charges, these ones, are placed at the edges A, B, C, and D of a square of size 3 centimeters as shown below. Then they said find the resultant force on the charge of positive 1 microcoulomb placed at the center of the square O, which is this, as shown above. So like I said, we have to redraw the diagram. So you'll come here and say that for me to answer the question, I have to redraw the diagram as it is given, then I allocate the directions of the forces. So now after drawing, they want the resultant force at O. At O, meaning there is a force due to charge at A, there's a force due to charge at B, a force due to charge at C, a force due to charge at D. But to get those forces, we need to get the separation. So we need this distance, we need this distance, and this distance. And because the square, the distance is the same. So you have to come and calculate those distances. So before we calculate the distances, let's first show the directions. So first of all, force at O due to charge at A. Remember, this is positive, this is negative, so it will be attractive in the direction. So we shall come and show it there. Then force on O due to charge at B, both are positive, there will be repulsion, meaning this one will go in this direction. So we shall come and show it there. Then force on O due to charge at C, both are opposite directions, so opposite charges, meaning they will be attractive. Then force on O due to charge at D, these are same like charges, so they will be repulsion. Okay, so after showing the directions, next is to calculate. But to calculate, I need to first get the separation. So to get the separation, I have to get the length of the whole diagonal SC, which is this. Then from there, remember that this diagonal is cut into 2 equal parts. So half of it will be my separation, which is 2.1213 centimeters. Then from there, I can now quote the formula and calculate. So force on O due to charge at A, the charges are 1 and 10. So that's why you see here. So I think realize that we are not showing the negative here because we are interested in the magnitude. So the formula is used to get the magnitude, then the law of electrostatics is what gives you the direction, as we have already seen here. So substitute and then use the calculator to get the answer. Then also get the force on O due to charge at B, so substitute and then use the calculator to get the answer they want. What about force on at O due to charge at B? So there we shall come on the next slide and say that force at O due to charge at C will be given by that, and it will be this. Then and lastly, force at O due to charge at D will be that. So what we are doing, we're substituting in the formula. So now that we have got all, we have to get the resultant. Now for the resultant, we have to resolve. So let us first see, we have to resolving horizontally and also vertical. So we shall start by resolving horizontally. This one will be that force cos 45, and this one will be this force cos 45, and they all be to the left, meaning to the right, meaning they will be positive. Then this force cos 45 will be to the right, to the left, and this force cos 45 will also be to the left, meaning they will be negative. So we have 2 positive and 2 negative. Therefore, we shall come and say that resolving horizontally, the positive ones, we shall start with the positive ones followed by the negative ones, but all of them have cos 45. That is why we have put it outside. Then use a calculator to come up with this value, and it is negative. That was resolving horizontally. What about vertically? Now vertically, so we shall go back to our diagram. Vertically, we have this force which is upwards, and this force which is upwards, and this is downwards, meaning these two which are upwards will be positive and these two which are downwards will be negative, and all will have sine 45. So we shall come here and say that vertically we have Fy, which is that. So the one upwards are the ones which are positive, and the ones downwards are the ones which are negative. So in the end we shall come up with negative force. Now, like I said, by sign convention, negative horizontal means it is to the left, and negative vertical means it is downwards. Therefore, we shall come and draw our triangle, starting with negative horizontal. So that is negative horizontal, followed by negative vertical. Then you trace a line from start to end. Now in this triangle, this symbol is very vital. Most students forget this symbol of right angle, but it is very vital. It is the one which enables you to use Pythagoras theory and SOHCAHTOA. So by Pythagoras theory, I come up with this squared plus this squared, everything under square root to give you this. Then from SOHCAHTOA, I come up with tan theta equal to this over this to give you theta as this. So an angle is easily written, is better if it is written into 2 decimal places. Then I'll come and conclude that the resultant force at the center O is this, in the direction this, below the negative horizontal. Below the negative because, like I said, it is in this quadrant which is below the horizontal and also on the negative side of the x-axis of the y-axis. So that was question 4. Now we shall go to question 5. Question 5 came from UNEB 2015 paper 2 question 10D and says 3 charges, these ones, of magnitude these ones, respectively, are situated at corners of an equilateral triangle 15 centimeters as shown in the figure. So this is an equilateral. Equilateral means all sides are equal. Then they want to calculate the net force on Q3. So there's a force on Q3 due to charge Q1 and also force on Q3 due to charge on Q2. Now because it's a triangle, we have to answer the question, we have to redraw the diagram. So we shall come here and redraw the diagram. Then you shall remember that an equilateral triangle, the angle, all angles are equal, 60, 60, 60, in order to add up to 180. Then these are the charges they gave us, these charges were given in the question. Now next is to show the forces. So this one, force on Q3 due to charge at Q1, both are positive, meaning it will be repulsive. So we shall come and show it there. So this angle is the same as this angle because they are corresponding. Then force on Q3 due to charge at Q2, opposite charges, so it will be attractive. So you come and show it. Okay, then after that we can now calculate the magnitude. So force on Q3 due to charge Q1 will be given by that. Then you substitute and get the answer, which is 4 Newton. Also, force on Q3 due to charge on Q2 is given by that formula. Then you substitute and then get 6 as your force. Now next we have to resolve. So resolving, I resolve horizontally. This one will be this cos this and this cos this. All are going to the left, to the right, meaning they will be positive. So it will be this plus this, because all of them have cos, that's why we have put it outside. And it will be 5 newtons. That is horizontally. What about vertically? Vertically, this one is going upwards and this one is going downwards, and it will be sine 60. Therefore, one will be positive, this will be positive, this will be negative. Therefore, we shall come here and so that resolving vertically, we shall have that. So we also have this one, and it is negative, meaning now we shall have to draw a right angle triangle. We shall start with a positive horizontal followed by a negative vertical. Now in this triangle, we don't show the sign, we only show the magnitude, because the sign is there to show you the direction, which is that arrow. Then you join from start to end. Okay, so now we have to use Pythagoras theorem to get the magnitude of the resultant, and also use SOHCAHTOA to get the angle. Then we can conclude. Okay. So that was question 5. Now we shall go to question 6, which says, the figure below shows the charges, these ones, placed at the corners B and C respectively of a triangle ABC of sides 8 cm, 10 cm, and 11 cm, which is as shown below. Find the electric force exerted on the charge of negative 2 microcoulomb when placed at A. So to easily answer the questions, you have to redraw. In fact, you must. There's no other option. So we shall come and redraw our diagram. So there is a force at A due to charge at B. These are opposite charges, meaning there will be attraction. So we shall locate that force. Then force on at A due to charge at C. These are like charges, so there will be repulsion. So to go this side. So this angle this angle and this one are alternating. This and this are corresponding. So remember, somewhere we shall need to resolve, meaning we have to get these two angles, alpha and beta. The good thing, we have all these three sides, meaning we can use cosine rule to get the angle, but that will be done at the part of resolving. So let's first start by getting the magnitude of the forces. So F is given by that formula. Come and substitute for FAB, this one, to give you this. Then also substitute for FSC to give you this. Then from there we can now think of the angles now before we resolve. So using cosine rule, 11, this one corresponds to this angle. That is why you see it here. So when I simplify further, make cos theta alpha the subject, and the angle will be this to 2 decimal places. So now that I've got the angle, I can now resolve. Okay, I also need beta. So beta, I'll use sine rule to give you that. Then I can resolve horizontally to give you this, which is this. Then also resolve vertically to give you this. So both are negative. So negative horizontal means to the left and negative vertical means downwards. So I'll come and draw my right angle triangle. Start with a negative horizontal followed by a negative vertical. Then you can join a line from start to end. Then you can use Pythagoras theory. So this right angle sign is needed. Use Pythagoras theory to get this magnitude and also use SOHCAHTOA to get the angle. Then you can conclude. So the conclusion is vital. You don't need to ignore it. So that was question 6. Now we shall go to question 7, which came from UNEB 2011 paper 2 question 9C, and says 2 pitch balls P and Q, each of mass 0.1 gram, now this is gram, are separately suspended. No, this was suspended from the same point by the threads 30 centimeters long. So the threads are of the same length. When the balls are given equal charges, note this word equal, they repel each other and come to rest 18 centimeters apart. Calculate the magnitude of the charge on each ball. So the balls have equal charges and similar charges. So you have to illustrate, like I told you, you have to illustrate here. So we shall draw the 2 pitch balls P and Q. And they told us they are separated by 18 centimeters, which is this 0.18 meters. And these are the threads 30 centimeters each. So you have to show the forces. Now because they are similar charges, there will be repulsion. One will go this side, another one will go this side. So this is F on P due to charge at Q, and this is F on Q due to charge at P, and they are repulsive but the same magnitude. That's why you see here F and also here F. The next is to show the weight. So the weight of this, remember it was grams. We have to change to newtons. You have to first convert to kilograms, then you multiply by G. So changing 0.12 gram to kilogram, I have to divide by 1,000 to give you 0.0001. Now this G is not the same as this G. It's not the same. I think you realize that here there is a space between the values, but here there is no space, meaning this one means acceleration due to gravity. So if it was a unit, there will be a space in between, but because there is no space in between, it is no longer a unit. It is acceleration due to gravity. Then also there will also be a weight here, same weight. So okay, the next will be tension in the threads. There will be tension here and there will also be tension here. There are 2 tensions, but our interest is on the forces which are acting on this pitch ball and also on this pitch ball. That is why it is okay to ignore these other tensions. Otherwise, if you want to make it complete, you should add the tension and the tension. But in order not to confuse you, you can deal with only this tension and this tension, because those are the tensions of interest. So to resolve, we need to get some angles. We need to get this angle theta. So we shall extract out this right angle triangle, which is here, which in order to help us to get the angle. So remember, they say this string is 30 centimeters. That's why you see here 0.3 meters. Then also the whole of this is 0.18. So when I divide by 2, I'll come up with 0.09 meters. So for triangle OHU, which is this, I can get sine theta. So sine theta is equal to opposite over hypotenuse. Therefore, theta is 17.46 degrees. And now that I've got this angle, I can easily resolve. So when I resolve vertically, it will be t cos that angle, because this angle is lying on the vertical. So t cos that angle is equal to the weight. We don't add this force because this force is entirely horizontal. Then I substitute for G. Remember I told you G is acceleration due to gravity, and in physics we take G as 9.81 for A-level physics. Then you make T the subject, and that will be the value of T. But the question said magnitude of charge on each ball, so we have not yet completed. Next is to now resolve horizontal. So horizontal there will be this force, which will be equal to T sine theta. So resolving horizontally, we shall have this equal to this. Therefore, we already know the T, so I can get the value of F as this. So I've got the repulsive force, but remember they want charge. So I'll come and remember that this force is equal to, from Coulomb's law, it is equal to Q squared. Now why am I saying Q squared? Because it is a product of two charges, Q1 times Q2, but Q1 is Q and Q2 is also Q because they are all the same charges. That's why there is Q squared here over R squared, which is the separation. So in this case I have F, which is that, and I have the separation, which is this, and the K is that. So I have only one unknown. Now my aim is to look for a way of making it the subject. So when I divide, I'll come up with Q squared as that, put square root to come up with the value of Q as that. And that's what they wanted. That was question 7. Now we shall go to question 8, which came from UNEB 2001, paper 2, question 9b, Roman 2, and says, two identical conducting balls of mass m are each suspended in air from a silk thread of length L. When the two balls are each given an identical charge of Q, they move apart as shown in the figure below. So it's the diagram. Then they said if at equilibrium each thread makes a small angle. Now note this word small. This word is very, very vital because there are some conditions which deal with small angles, as we shall see in the solution. With the vertical, show that the separation x is given by this, where this is the permittivity of air. So remember I told you we use epsilon naught to mean permittivity of air or free space of vacuum. But in this case, because it was specified that this one means permittivity of air, then you don't again replace it. That would be Weizsäcker. Okay, so we still have to redraw the diagram such that we can show the forces acting on each ball. So we shall come and redraw what is given, after which we shall show the forces. Okay, so like we said, there will be repulsion, so one force will go this side and here to go this side. That is one. Next is weight. So there's this weight mg. Now this g is not grams, this g is acceleration due to gravity, and the reason is because there is no space in between. So weight is always mass times acceleration due to gravity. So when you are writing it, make sure you don't leave any space in between. Then also here we put that weight. The next is the tension, and also tension here. Like I told you, it is okay to put this tension, but our interests are the forces on these two balls or conducting balls. That is why I can choose to ignore this other force, this other tension. So I need an angle, so that angle is theta. So I'll extract out this right angle triangle. So you realize that the whole of this is x, meaning half of it is half x, and this length was given as L. Okay. Now from triangle OAB, we shall come and say that sine theta is equal to 0.5x over L, which is here. Simplify to come up with x over 2L. Then for small angles, that's why I told you that you should note the word small angle. So this word small angle gives you a certain condition. So for small angles, sine that angle is approximately equal to that very angle. That means that this sine will be equal to theta, therefore approximately equal to theta. So theta is equal to that. Okay, we have dealt with that condition. Now let's go to resolving. Now when I resolve vertically, t cos theta, cos because the angle is lying on the vertical, is equal to mg, called equation 1. Resolve horizontally also. So resolving horizontally, t sine theta is equal to f. But I already know that f is equal to q squared 4 pi epsilon x squared. I think you can know where this formula is coming from. So in this case, we are not using the k because the required expression has epsilon in it. That's why you're using 1 over 4 pi epsilon. So when I substitute where there is f, I'll put there that value of f to give you equation 2. So I have two equations. There is this and there is also this. Now when I divide the two equations, I'll come up with that. Then this and this cancels, this and this gives you tan to give you that expression. Then I also remember that for small angles measured in radians, tan theta is, okay, let me write it. Tan theta approximates to tan an angle approximates to that very angle. So that means that tan theta is approximately equal to theta. But remember, we already got theta. If you look at this previous slide, we had got theta as x over 2L. So that is why I'm writing it here, x over 2L. Therefore, from there, I'll come here and substitute where there is tan theta. I'm going to put there this value, which is here, and this one remain as it is. Then from there, now my aim is to make x the subject. So what I'm going to do, I'll first cross multiply. This goes this side to give you this x cubed. Then I'll divide, okay, I can simplify, divide by 2 on both sides. Then next is to divide. So take all these ones this side to remain with x cubed. And lastly, put the cube root, and that will be the required expression. Okay, so now we have been dealing with permittivity of free space. But sometimes they may not give you permittivity of free space. They can give you another medium. So how do you deal with that? So in that case, we need to know a term called relative permittivity, or in other words, dielectric constant. So these two words mean the same. They can either use the word relative permittivity or they use the word dielectric constant. Now what is it? Relative permittivity is the ratio of permittivity of a material or medium to the permittivity of free space. Remember, this permittivity of free space is a constant. Therefore, and therefore, that means that relative permittivity, which is epsilon r, is equal to epsilon m, which is permittivity of a material, over epsilon naught, which is permittivity of free space. What does that mean? It means that always, or in most cases, they will give you the relative permittivity, and it will be you to get the permittivity of that medium. So when given the relative permittivity, I have to cross multiply to get this expression, that permittivity of a medium is equal to relative permittivity multiplied by permittivity of free space. So when given this one, you can get this one because permittivity of free space is a constant. So in that case, we no longer write epsilon naught here, but we write epsilon m to mean permittivity of that medium where the positive charges are situated, where the point charges are situated. So epsilon m, I already know that it's equal to this, so I'll come and substitute to give you this. Then from there, I remember that this one alone, 1 over this gives you k. That is why I'm writing this k here. And I'll add on these two charges, and also here I'll be left with this one, which is here. So this is now our new formula when they give you relative permittivity. And with that, we shall now be able to do our question 9. Question 9 says, charges this and this are placed in liquid. Note this word liquid. So it is no longer air, it is no longer vacuum, it is no longer free space, but it is now liquid. Of relative permittivity 9.0 when they are separated as shown below. Find the resultant force on the charge at B. So charge at B is due to charge at A and also due to charge at C. So the first thing to do is, okay, now if I use these two charges, the separation is 2 centimeters and the charges are these ones, then you should realize that the opposite charges, meaning they attract. Because we're interested in the force at this charge, so this one will attract and it will go in this direction, which is to the left. So I'll come here, like I told you, charges in a straight line, you don't need to redraw, so I'll just come and quote the formula and substitute. So quote the formula, then substitute. So force at B due to charge at A will be equal to this. That is K. This is one charge, another charge, relative permittivity, and separation. It is to the left because it was attractive. What about force at B due to charge at C? The force at B due to charge at C, these are like charges, meaning they will repel. So when they repel, this one goes this side. So it will also be to the left. So come and substitute and write and get the value to the left. Now both are in the same direction, left, left, meaning the resultant force will also be to the left. So we shall start by defining electric field intensity at a point. So this is the force, know this word force, acting on a positive charge of 1 coulomb. So this word is vital, positive charge of 1 coulomb, placed at a point in the electric field. So this is the force, and remember in the previous video we saw that force is a vector quantity. That means that also electric field intensity is a vector quantity. Therefore, because the one charge has to be positive 1, that is why we divide. So electric field intensity is equal to electrostatic force divided by magnitude of charge in the field. So one charge will be creating the field, and the second charge will be positive 1. So like I said, because force is a vector quantity, it implies that even electric field intensity is also a vector quantity and is measured in newtons per coulomb. Newtons is because of this force and coulomb is because of this charge. So when I divide, I'll come up with newton per coulomb. So that will be the SI unit which we shall use for electric field intensity at a point. So we shall try to derive a formula for electric field intensity at a point. So we shall consider a point charge Q placed in a medium of permittivity. So this charge will be the one creating the electric field. Let the test charge Q naught be at a distance r from the charge Q. So by Coulomb's law, we shall know that the force between these two charges will be given by this Q naught over 4 pi epsilon r squared. Now we're not putting epsilon naught because they didn't specify that the permittivity is free space. So you have to just put epsilon. And that is also why we are not using K. But we already know that electric field intensity is equal to force over magnitude of charge. So it will be force over the charge in that field. Note that we're using Q naught and not Q because Q is the one creating the field, and Q is the one creating this field, and Q naught is the charge in that field. So for this case, we are not using 1, but at the end we shall make it 1 by dividing. So that is why we are dividing by Q naught. So when I substitute for F, I'll come up with this over this. Then you realize that this and this can cancel to come up with this. So that will be the expression for electric field intensity at a point. But most questions, they use free space as the permittivity or as the medium. Therefore, we shall say that in free space, electric field intensity will be given by when we have now epsilon naught. And like we already said, 1 over 4 epsilon naught is equal to K. That means that all of that will be replaced by K. Then you remain with Q and R squared in the denominator. And you already saw that K is equal to 9 exponent 9 meter per farad in the previous video. So this is the formula we shall be using more frequently, and remembering that K is equal to that. So like I told you, this constant is also given in the table of constants in an examination. There's no need to memorize it. So now that we have seen the formula for electric field intensity at a point, let us go through some of the questions. Question 1 came from UNEB, November 1998, paper 2, question 9A Roman 2, and it says, the electric intensity at the surface of the earth is about this. So this is another SI unit for electric field intensity and points towards the center of the earth. Assuming that the earth is a sphere of radius this, find the charge held by the earth's surface. So the earth is a sphere, so this will be like this, and there will be a charge on the surface of the earth which points towards the center. So this will be the R, and here there will be the charge. Here they give you the potential electric field intensity. Therefore we know that electric field intensity is that, then K is this, and the charge is what they want, they don't know it. Then the separation from this to the center is given also, so we shall put it here. Now with this, I think we realize that we have only one unknown, therefore we shall come and say that Q is equal to this. So it is better to write your answer in scientific notation. So that was question 1. Now we shall go to question 2, which came from UNEB 2006, paper 2, question 9B, and says 3-point charges, these ones, are arranged in line as shown in figure above. So that the charges, find the electric field intensity at point P. So just like it was for electrostatic force, even here there will be electric field intensity at P due to charge this, and also electric field intensity at P due to this charge, and also electric field intensity at P due to this charge. Now because it is also a force, we shall consider like charges. For example, here when they talk about electric field intensity at a point, you should remember that they consider a positive charge at that point. The rest of the charge is what creates the electric field. So here there is positive 1. For example, this and this like charges, so there will be repulsion, meaning that electric field intensity will be in this direction to the right. Then for this and this, they are opposite charges, meaning the electric field intensity will be in this direction. Then for this and this, they are like charges, so the electric field intensity will be in this direction. So the formula will be used to calculate the magnitude, and the law of electrostatics will help us to get the direction, just like it was in the previous video. So I shall come here and say electric field intensity is given by that formula, therefore I can now substitute. So substitute electric field intensity at P due to charge at R, substitute for K, then for Q at R, then for the separation. So the separation from here to here, it will be this plus this plus this, which will be 1 meter. That is why you are seeing me here adding this plus this plus this to come up with this. Like I said, it's easier, it is advisable to write your answer in scientific notation. So it will be to the right because of repulsion. Then also electric field intensity at P due to charge at S. So charge at S, if you look at it, charge at S, so this is S, we didn't label, but this is RS. So P and this one, they are opposite charges, so because here there is a positive 1 Coulomb, so there will be attraction, meaning it will be to the left. Then the separation will be this 0.2 plus 0.3. That is why you are seeing it here. Then next is electric field intensity at P due to charge at T. So this is 0.3, the separation is to the right. Why? Because if you look at this, this is positive and here there is positive 1, meaning there will be repulsion, which will take it this side. And the separation is 0.3. So that is why we are writing here to the right. Now that we have got all the individual electric field intensities, we have to get the resultant electric field intensity at P. So the resultant will be got by adding and subtraction. For example, here we shall take this. If you look at this, when you add this right and this right, you add them and compare them with this, you realize that the one of the right is bigger, meaning they will be positive. So this will be positive. This one is left, it will be negative. This is right, it will be positive. And when I use a calculator, I'll come up with this, and the answer will be to the right because right was the one which is bigger. And that's what they wanted. Then question 3 came from UNEB 1994, paper 2, question 10D, and says, find the resultant electric field intensity at point P due to charges shown in figure below. So these are the charges, and like I said, as long as it's a triangle, rectangle, square, you have to redraw the diagram. So we shall come here and first redraw the diagram. So after redrawing, next is to show the electric field intensities. So the one at P, due to charge at A, remember when they talk about electric field intensity at a certain point, it means that at that point there is a charge of positive 1. Therefore, positive 1 and this positive, there is a repulsion, meaning to go in this direction. So we shall come and show it there. That is electric field intensity at P due to charge at A. What about due to charge at B? So this is negative, and here there will be positive, meaning there will be attraction. So it will be in this direction. So we shall come and put it there. Then what about due to charge at C? So positive, here there's also positive, there will be repulsion, and it goes in that direction. Now this 45 is because it is a square. If it was a rectangle, you cannot put 45 here. You would calculate using SOHCAHTOA. So now that we have shown all the electric field intensities, we can now go ahead and look for a way of getting the resultant. So to get the resultant, you need, to calculate, to get the magnitudes, you need the separation of from here up to here. So let's first get it, PB, to be by Pythagoras theory, 0.2 squared plus 0.2 squared, everything under square root to give you this. Now we are leaving it as a square root because in the formula, there will be a square somewhere, meaning the square root will also go away. So just start electric field intensity at P due to charge at A. The charge is this. It is microcoulomb, so we have to change it to coulomb. Then the separation is from here to here, which is this. And K, we already know that's 9 exponent 9. So when you use a calculator, we shall come up with this. What about electric field intensity at P due to charge at B? So the charge is this, which I convert it to Coulomb. Then the separation is from here up to here, which is this. And K is 9 exponent 9. So still you shall come up with this. Then the electric field intensity at P due to charge at C. The charge is this. The separation is from here up to here, which is this. And K is 9 exponent 9. So use a calculator, you'll come up with that. So like I said under Coulomb's law, here we shall not show the directions because they are already shown on the diagram. So drawing the diagram is a must. Now next will be to resolve. We shall resolve horizontally. Resolving horizontally, there is this, and also there is this. The component of this is to the left, meaning it will be negative. So it will be this cos this 45 degrees. Now this one has no horizontal component because it is entirely vertical. Therefore, we shall come here and say that resolving horizontally, we shall come up with this minus this cos 45. So we covered resolving under mechanics of physics, paper 1. So when I use a calculator, I'll come up with this as the electric field intensity. So this negative is needed here to help us to show the direction. So that was horizontally. What about resolving vertically? So resolving vertically, this upward will be positive, but here the component of this will be negative because it is downwards, and it will be this sine this. Now this one is entirely horizontal, meaning it has no vertical component. Therefore, we shall come here and say that the vertically it will be this minus this sine 45 degrees, and to give you this. The negative is needed because it helps us to draw the right angled triangle. So by Pythagoras theory, the magnitude will be of the resultant will be this, but we also need direction because it is a vector quantity. So we shall draw a negative horizontal, which is to the left, followed by a negative vertical, which is downwards. This right angle sign must be seen. Then you join from start to end, and that will be the resultant electric field intensity at P. So our aim is to get this value of theta, so we shall use SOHCAHTOA. So this one is just a repetition, you can ignore it. Then tan theta will be opposite over adjacent, which is this, and gives you 45 degrees. Therefore, we can conclude that the resultant electric field intensity at P is this, in the direction this, below the negative horizontal. So I believe by now you know why we are saying below the negative horizontal. It was explained under Coulomb's law. Then question 4 came from UNEB 1995, paper 2, question 8b, and says 3 charges, these ones, are placed in a vacuum. Vacuum means free space. At the vertices P, Q, and R, as shown. So P, Q, R of sides this and this. So this is now a rectangle, no longer square, as shown in the figure above. So this is the figure. Calculate the electric field intensity at S at this point. So still the first thing to do is to redraw the given diagram. So redrawing is a must. So what I'm redrawing, shall show the directions of the electric field intensity. Like I said, if they want intensity at S, it means that you consider a positive charge of 1 coulomb to be at that point. Now, due to P, both are unlike charges, meaning there will be attraction, so to be in that direction. Therefore, we shall come and put it there. Then, due to Q, both are positive, so to be a repulsion going in that direction. So here I think we realize that we're not putting 45 degrees here because it is a rectangle. Then due to R, also like charges, so there will be repulsion going that side. Okay, now that you have shown that, next is to go to the calculations. We shall first get the separation QS, which is by Pythagoras theory, this square plus this square, everything under square root to give you 5 centimeters. Then also the angle, this angle alpha. Remember, this is the rectangle triangle, meaning that here, this will be the opposite, and this will be the adjacent. So opposite is 3, adjacent is 4. Remember, tan is opposite over adjacent, meaning angle is this degrees. So to 2 decimal places, angles are accurately measured to 2 decimal places. Then now we can get the magnitude. So from using this formula, that electric field intensity is equal to KQ over R squared. So we shall come and substitute ESP. We use this as a charge, and the separation is this. We convert it to meters. Use a calculator to come up with that. So it's advisable to use scientific notation. Then ESR, we use this as a charge, and separation is this, converted to meters to give you that. Then ES2 separation is from here to here, which is this, and the charge is this. So use the calculator to come up with this. So just like it was under Coulomb's law, here we don't put the negative sign on in the formula because this formula helps us to get only the magnitude. Then the direction will be got by the law of electrostatics. So now that you have calculated this, this, and this, next is to resolve. So when I resolve horizontally, I'll come up with that to give me this. The negative has to be seen. Horizontally meaning that this to the right is positive, to the left is negative. Then resolving vertically, upward is positive. So all are upward, so that is why they are all positive. Then you can use Pythagoras theory to get the magnitude of the resultant and then draw a right angle triangle, so negative horizontal to the left and positive vertical upwards. The right angle sign has to be seen. Then you join from start to end. Our interest is to get the value of theta, so we shall come and say tan theta is equal to this over this, which gives you this as the angle. Now that I've got the magnitude and direction, I can state in that form. And basically that's what they wanted. Then question 5 came from UNEB 2002 paper 2 question 9c and says 2-point charges A and B of charges this and this are separated by a distance of 8 centimeters along the horizontal as shown above. Find the electric field intensity at P. So they put a charge here which is this and a charge here which is this, and they want intensity at P. Now because it is a diagram, we have to redraw. Okay, so this one shows that it is an isosceles triangle, meaning this angle is equal to that angle. So because here there is positive 1 and this is also positive, so there will be repulsion, that's why it goes that side. And this angle will be equal to this angle, corresponding angles. Then also this with this, positive, meaning there will be repulsion going this direction, and this angle will be equal to this angle, so they are the same because it's an isosceles triangle. Then next is to get the magnitude. Electric intensity is given by that formula. So get intensity at P due to charge at A, and to be that. So the separation is 5, convert to meters, and the separation is this one, convert to meters. Then also the charges here, convert to Coulomb. You'll come up with that. Then also intensity at P due to charge at B. Separation is this and the charge is this. So I've got the magnitudes. Now we have to get this angle. So by cosine rule I can choose to use this and this, meaning that 5 squared is equal to this squared plus this squared minus 2 times this cos alpha, which is this statement. Next is to simplify and look for a way of getting alpha. So alpha will be that to 2 decimal places. So now that I've got alpha, I can go ahead to get my resultant by resolving vertically and horizontally. So horizontally, this is to the right, this is to the left. Vertically, all are upwards. Therefore, we shall come here and say that resolving horizontally, one will be to the right, another one to the left, but have the same angle. So it gives you this. Then vertically, all are upwards, meaning to be addition, to give you this. Then resultant, magnitude of the resultant is that by Pythagoras theory. Then you draw a triangle, negative horizontal to the left and positive vertical upwards. Right angle sign has to be seen. Then you join from start to end, and that will be your resultant. But I'm interested in this angle, so I'll use tan theta equal to this over this to give you that as the angle. Therefore, you can come and conclude. And that's what they wanted. Then question 6 came from UNEB, November 1998, paper 2, question 9b, and says 2-point charges, this and this, are separated by this in air. So air means free space, as shown below. Find the electric intensity at point X at distance 20 centimeters from each charge. So this is also an isosceles triangle and is somewhat similar to the one we have just done. The only difference is that in the previous one, both charges were positive, and here one is positive and another one is negative. So shall again redraw. If given a diagram, you have to redraw it. There is no way you can bypass that. So we shall put we shall put intensity at X due to charge at A, and to be repulsion, that's why it goes the side. Then also due to charge at B, it is attraction, that's why it goes the side, it is attracted. So this angle and this angle are similar because they are corresponding. This and this are similar because they are alternating. We are using alpha on both sides because this is an isosceles triangle. So shall come and calculate the magnitude. This one, X due to charge at A, separation is this, convert to meters. The charge is this, convert to coulombs. Then you'll come up with that. Then due to charge at B, separation is this, convert to meters. Separation, sorry, the charge is this and separation is this. So then you'll come and use a calculator. So now by cosine rule, we shall again use this 20 squared is equal to 20 squared plus 10 squared minus 2 times 20 times 10 cos alpha, which is this angle here. The next is to simplify until you get alpha, the subject. So when I simplify, I'll come up with alpha as this, to 2 decimal places. So angles are easily expressed to 2 decimal places. So now that I've got the angle, I can now resolve. So both horizontally, both are to the left, meaning they'll be positive, but vertically, this one will be upwards, this will be downwards. So one will be positive, the other will be negative. So horizontally, we shall add both of them. They have the same angle to give you this. So resolving vertically, one will be positive, another one will be negative. So it gives you 0. Now because it is 0, it implies that the component is entirely, the resultant electric intensity is entirely horizontal. So shall just come and conclude that since the vertical component is 0, it implies that the electric field intensity at X is this, acting horizontally to the right. Then question 7 came from UNEB, March 1998, paper 2, question 9C, and says 2-point charges, this and this, are replaced in air, that is free space, at points P and Q, as shown in the figure above, which is this. Determine the electric field intensity at R. So like we have always done, we have to redraw the diagram. The next is to show the electric field intensity. So here we shall consider a positive charge of 1. Therefore this and this repulsion, because they are all like charges, that's why it is going in that direction. Now this one is no longer isosceles and is also not equilateral, so these angles will be different. So this will be alpha because of this. Then also due to this charge there will be attraction because of unlike charges, so it will go in the direction, and this will be beta beta alternating angles. Then we can now calculate our magnitudes first. So using the formula, intensity at R due to charge at P, this will be the charge used and this will be the separation converted to meters. Then you come up with that. Then at R due to charge at Q, this will be the charge used and this will be the separation. Then you come up with that. Then you have to get the values of sine and alpha and beta. So because this is 13, 12, and 5, this is right angled. I think it was given in the question. So this is the right angled triangle, meaning I can use SOHCAHTOA. So with this angle here, if I use sine, it will be opposite over hypotenuse. That is why you see here 5 over 13 to give you this. Then from there, I know that angles of the triangle add up to 180. So this is already 90 is off, meaning these two add up to 90. That is why beta will be 90 minus alpha to give you this. So what I'm getting that, it means I can resolve. Now horizontally, this one is to the left, to the right, and this one is to the left. But vertically, all are downward. So resolving horizontally, we shall come up with this minus this to give you that. Then vertically, all are downward, so there will be negative, negative to give you a negative value. The next is to draw a right angle triangle, negative horizontal, Pythagoras theory first, to come up with the magnitude of the resultant. Then draw a right angle triangle, negative horizontal to the left and negative vertical downwards, and the right angle sign has to be seen. Then draw from a line from start to end, and that will be your resultant. But our interest is that angle theta, so we shall come up with tan theta is equal to this over that to give you this as the angle. The next is to conclude. So we can now start electric potential at a point. So electric potential is the work done, know this word, work done to move or transfer a positive charge of 1 coulomb. So the charge has to be positive 1 from infinity to a point against the electrostatic field. Remember previously we covered electric field intensity and we said it is a force. But now when it comes to electric potential, we are saying it is work done. Now what we know about force and work is that force is a vector quantity, and that is why electric field intensity was a vector quantity. But when it comes to work, work is a scalar quantity, meaning that electric potential is also a scalar quantity. Scalar means that we are not interested in the direction, we are interested in the magnitude, as we shall see in the calculation. So the SI unit, this is the scalar quantity, and the SI unit for electric potential is volt, abbreviated as capital V. Now what we are going to do, we shall do some derivation, because this is now totally different from what we have been doing. Previously we did electrostatic force and electric field intensity, which were both vector quantity, but now this one is a scalar quantity. So let's do some derivation of the formula which we shall be using. So we shall consider a positive charge of 1 coulomb placed at point B at distance x from charge Q situated in a vacuum as shown below. Now this derivation we are writing is also examinable, so I think you should realize that that every symbol or letter we are going to use is being defined. So when one reads the statement, he will know that x means distance from charge Q and Q means charge. So endeavor to describe the symbols or letters you are using. So now we can draw our sketch with Q here. The distance is r, and our part B is here, and the distance is x. And this will be the direction of a force. and this will be a small change in distance x. So we are putting direction because in the formula they said against the electrostatic field. Now against means it comes from somewhere so far, infinity, up to a point in the electrostatic field. So we shall come and say that the electrostatic force F experienced by a positive charge of 1 coulomb due to charge Q is given by this formula. Remember, this is the formula that Q1 times Q2 over 4 pi epsilon naught r squared. Now in this case we are using x because from, if you look at this diagram, at this point, now this is where our charge of positive 1 is, and this is another charge. So the force between the two will be Q1 times Q2, where Q2 is 1 coulomb, Q1 is 2, and the separation between the two will be x. We are not using r, we are using x because the charge is at this point B. So now as you shall come and say that assuming that the force on Q on the 1 coulomb charge remains constant over a small distance. Remember, this distance is a very small distance. Now the assumption, this assumption is needed in the derivation. So the assumption is that this force does not change over a very small distance. Against electrostatic repulsion, the work done is given by, so against electrostatic repulsion means that this small distance, let's go back to the diagram. Against electrostatic repulsion means that you're moving it from here in this direction. If you move it in the other direction, it will be in the direction of the electrostatic force, which is not okay because our definition wants the word against. So it must be in this direction. So we have said that the force remains the same, therefore the work done will be force times distance moved, and the distance is negative small change in x. Now why is it so? It is because these two are in opposite direction. Remember, force was to the right, but we are moving the charge to the left, meaning they are in opposite directions and they will be distinguished by a change of sign. Now after that I will come and substitute for f because we said the assumption that f remains the same. So I'll come and bring this one and put it here as you have seen here. Then this negative can be pulled out because it's a multiplication, and this one will remain the same. Now this was small work done. What about the total work done? So total work done in bringing a positive charge of 1 coulomb from infinity to a point A at distance r from the fixed point Q, from the fixed charge Q, is the electric potential at A and is given by, so when they want the electric potential at A, they want the work done in bringing a positive charge of 1 coulomb from infinity to that point A. So in this case, if I look at this, now this was used as a test to get the general expression for small work done, but our interest must be, if you look at this, from infinity up to a point in the against the electrostatic field. So I have to move it from infinity somewhere and bring it up to a point in the electrostatic field, which is now point A. So when I bring it here, it implies that the distance is from the distance initially it was infinity up to a distance which is now r. Therefore I'm going to integrate. Let's see how to integrate. So I'll come and integrate from infinity up to r. So I'll integrate what? Integrate this small work done. So and it's given with this expression. So I'll come and put the negative there. Then I'll put this expression. Okay, let's start with this one, which is here. Now here to a small change in x, but when it comes to an integral, we use dx. You should note that. Then from there, I realize that there are some letters or symbols which are constants. So for example, chu is constant, is not changing. These two are not changing, but this one keeps changing. Therefore, these ones, I'll put them outside. That is why you see chu over 4 pi epsilon naught outside, because they are constant. Then I remain with only x squared, which is varying. And that's what I'm going to integrate, because I'm integrating with respect to x. So now integrating 1 over x with respect to x will give you negative 1 over x. So this negative, okay, let's just leave it there. So this one was a constant, we saw it. Then this one I've integrated. Now next is to substitute the limits. Now when I substitute the limits, first put this r where there is x to come up with negative 1 over r. Then minus, put infinity where there is x to come up with negative 1 over infinity. Then from there, you realize that any number divided by infinity is 0. So the whole of this is 0. Meaning that I'm going to multiply this one with this. When I do that, I'll come up with this negative, and this negative is positive. That is why you don't see any negative here. Then this one is here, and the whole of this is here. Then there is this arrow which is there. So basically that is the derivation of electric potential at any point in the electric field. Yeah. And that is the formula we shall be using. So I think you remember, so if here we shall say that if a positive charge of 1 coulomb is replaced by a positive charge Q1, it implies that the total work done, W, in bringing the charge Q2 from infinity to a point A, a distance r, from the fixed charge Q, is the electric potential energy. Now here there is a difference. Previously, we saw that one charge must be positive 1. If that is the case, then we are talking about electric potential. But when the charge given is not positive 1, the charge being transferred from infinity to a point against electrostatic field is not positive 1, we shall talk about electric potential energy. Therefore, that means that here, instead of putting 1, like we said, 2 times 1, we shall put Q1 times Q2, which is this. So here it is no longer 1 coulomb, it is now a certain charge. And when it is not 1 coulomb, that's when we talk about electric potential energy. In other words, it is given by electric potential times the charge being transferred. So that was the electric potential, but there's also another formula for electric potential difference between 2 points. So we have seen electric potential and electric potential energy. What about electric potential difference? So electric potential difference between 2-point charges is the work done to move a positive charge of 1 coulomb from one point to another in the direction of force. Now here they are using the word in the direction of force. It is no longer against. So you should know that for electric potential it was against the direction of force, but here it is in the direction of force. So those definitions are very vital because they are also examinable. So previously in electric potential, it was supposed to be moved from infinity to another point. But when it is potential difference, it is just moved from point to point within the electric field. And the SI unit for electric potential difference, the same as that for electric potential, which is volt. So shall try to look at the formula for electric potential difference. So shall consider a positive charge of 1 coulomb placed at a point A at distance r1 from a fixed point charge Q situated in a vacuum as shown below. So we shall try to illustrate that. So this is charge Q, this is point A, which is a distance r1 from Q, and this is point B, which is a distance r2 from Q. And this will be the direction of the force. So the total work done in bringing a positive charge of Q1 from point A to point B is the potential difference, which is denoted by VAB, between 2 points A and B, and can be got as follows. Now you should note that we are moving in the direction of the force. For example, if you look at this diagram, previously it was against the electrostatic force, so it was being moved in this direction. But now it is in the direction of the force, therefore it has to be moved from A towards B, which is in the same direction as that of the force. So that's what this word "in the direction of force" means. And you must specify the medium, vacuum in this case. So you already know that electric potential at A is given by that formula. Then also electric potential at B is also given by that formula. What changes is the distance from the fixed charge. Therefore, potential difference will be got by subtracting, just like the word difference is. So VAB will subtract VA minus VB to give you this. And that will be the formula for potential difference. Now here, just like it was under electric potential, even here, if the positive charge of positive 1, the charge of positive 1 is replaced by a positive charge of Q1, it implies the total work done in moving a charge Q1 from A to B is given by this. So now the total work done is no longer electric potential difference. We just call it work done. And to be charge being moved times potential difference. We already seen that this one is equal to this minus that. So basically those are the three questions asked: electric potential difference, electric potential energy, and work done in moving from point to point. So with those formulae, we can go through these questions. Question 1 came from UNEB 2003 paper 2, question 10 Roman 2, and says 3-point charges, these ones, of magnitude, these ones, respectively, are situated along a straight line as shown in the figure below. So this is the diagram. This is Q1, which is 5 microcoulomb, Q2, which is 6 microcoulomb, and Q3, which is negative 20 microcoulomb. Calculate the electric potential midway between Q1 and Q2. So midway means from here to here it is 5 centimeters, and from here to here is 5 centimeters. So we shall try to redraw the diagram because they have given us a certain position which was not initially in the diagram. Okay, now we are converting from centimeters to meters. That's why you are seeing here, instead of writing 5 centimeters, we are writing 0.05 meters. Even here instead of 10 centimeters, we are writing 0.1 meter. So Q1 was this, Q2 was this, Q3 was this. And the formula first is quoting the formula for electric potential. I think you know what K means. It is 1 over 4 pi epsilon naught. So this is a short way. If I replace 1 over 4 pi epsilon naught, I'll come up with K Q1 Q over R, where Q is the fixed charge. So with that, I can get electric potential midway between Q1 and Q2. Now midway, now where is this thing coming from? We are writing this because we said electric potential is a scalar quantity, meaning we are not interested in the direction. Previously, we could do them separately. For example, electric potential at this, electric field intense at this due to this charge, at this due to this charge, at this due to this charge, because the directions were different. But now that we are not interested in the directions, we shall add the whole of it at once. So this is common to all. What is changing is this Q and R, and that's what we are putting inside. For example, due to this charge, we shall put this here, and the separation will be this, dA. And due to this charge, we shall put this here, and the separation will be dB. And due to this charge, we shall use this, we have put Q3 and also the distance from D to C, which is this. So after quoting the formula, next is to substitute. So you have substitute for Q1, convert to Coulomb, then the separation, substitute for Q2, separation, substitute for Q3, and separation, which is from here up to here, which is this. Now what you should realize is that here when the charge is negative, we also put the negative there, because this is now a scalar quantity. Previously the negative will help us to show the direction, but now this is a scalar quantity. So when I use the calculator, the whole of it will be this, and that's what they wanted. Next will be question 2. Question 2 came from UNEB 1997, paper 2, question 9b, and says the figure below shows charges, these ones of these magnitudes, arranged in a straight line in a vacuum as shown below. Calculate the potential energy at Q2, potential energy at this. Then 2, what is the significance of the sign of the potential energy in Roman 1? Now we are using the word potential energy because at this Q2 is no longer positive 1. If you look at this, because this is this and this is positive 2. So because it is no longer positive 1, we cannot say electric potential. What we say is electric potential energy. That is why we are seeing this word potential energy. So I shall choose to redraw the diagram. So now that I've done the diagram, we can get our electric potential energy. So first of all, electric potential is given by this formula. So that's what you're going to get, because potential energy is electric potential times the charge at that point. So electric potential, we shall consider a charge of positive 1 first. And when you do that, this will be the formula. I think by now you're aware of it. You have to add up all the charges. There is this one, there is this, there is this, which is here. Now R1 is this separation, R3 is this separation from here up to here, and R4 is this separation from here up to here. So we shall substitute for Q1, Q3, and Q4. Substitute for R1, R3, and R4. So when you use a calculator, like I said, what is negative remains negative. When you use a calculator, you get negative this. So the negative is needed in electric potential. Now that is electric potential. That means that electric potential energy, you multiply that charge at that point with the electric potential at that very point. So the charge was positive 2 Coulomb and the electric potential is negative this. So in a substitute, I'll come up with negative that as the answer. So potential energy will be in joules. That was Roman 1. Then for Roman 2, they said, what is the significance of the sign of the potential energy in Roman 1 above? So in this case, the sign is negative, and the question is, why is it negative? So the negative sign means that work is done by the electric field to bring up charge from infinity to that point. So it is from infinity up to that point, and that is why it is a negative. It is because work is being done by the electric field to bring the charge from infinity to that point. So that was question 2. Now we shall go to question 3, which came from UNEB 2019 paper 2 question 8c, and says, in figure 3, points P and Q are at distances 30 centimeters and 20 centimeters as shown here, from a point charge of 4.0 microcoulomb respectively. Calculate Roman 1 electric potential difference between P and Q. Then Roman 2 energy required to bring a charge of positive 1 microcoulomb from infinity to a point Q. So let's start with Roman 1 electric potential difference between P and Q. Potential difference means you have to get the electric potential at P and also at Q, and you subtract the two. So electric potential is given by this formula. Therefore, electric potential difference, electric potential at P is given by that. So case that the charge was this, change to Coulomb, and the separation was this. So you come up with this as the electric potential at P. Do the same for electric potential at Q. Case that charge is the same and separation was 20 centimeters, convert to meters to come up with this as the electric potential at Q. Therefore, electric potential difference will be, you subtract the 2 to come up with this. So that was Roman 1. Now we shall go to Roman 2. Roman 2, they say the energy required to bring a charge of positive 1 microcoulomb from infinity, know this word, from infinity to a point Q. So if it is from infinity to a certain point, we shall use electric potential. If it was between these two, we would have used potential difference. But now it is from infinity to a point Q, meaning we shall use electric potential at Q multiplied by that charge being transferred. So we shall come here and say that electric potential energy required will be charge transfer times electric potential at Q. So the charge was 1 microcoulomb, you convert to Coulomb, and the electric potential was this, which is here. You come up with this as the answer. Then question 4 came from UNEB 2013 paper 2 question 10 Roman 2, and says 2-point charges of this charge are placed 10 centimeters apart as shown in the figure below. So these are charges and they are placed 10 centimeters apart. Calculate the electric potential at P. So at P there is this charge, due to this charge, and also due to this charge. But because we are not interested in the direction, we shall just add all of them. So due to this charge, the separation is 10 centimeters, and also due to this charge, the separation is 10 centimeters. Therefore, you shall come and say that electric potential is given by that formula. Therefore, the total electric potential at P, we shall add due to charge at A and due to charge at B. And the charges were the same, positive 1 exponent negative 5, positive 1 exponent negative 5. Separation were also the same, 10 centimeters convert to meters, 10 centimeters convert to meters. And that would be the answer they wanted. Then question 5 came from UNEB 2010, paper 2, question 9b, and says, two charges of magnitude 6 microcoulomb and negative 10 microcoulomb are placed at the corners of a rectangle ABCD as shown in the figure below. AB is 6 centimeters, BC is 4 centimeters, so AB is 6 and BC is 4. Point E is the midpoint of AB, meaning if this is 6, then from here to here to be 3, and from here to here to be 3. Find the work done in taking a point charge of 1.6 exponent negative 10 Coulomb from point D to point E. That means that we shall have to get first electric potential at D and also electric potential at E, then get the difference. So that means that at D we already know the distances, but at this one we shall need this separation. Therefore, to get that separation, we shall first redraw the diagram. Then you can calculate this separation CE because we shall need it. Use Pythagoras theory for this right angle triangle. 3 squared plus 4 squared, everything under square root to come up with 5 centimeters. Therefore, electric potential at D will be due to this charge, which is here, and also due to this charge, which is here. Then we can substitute and get the potential at that point. Then also electric potential at E, it is due to this charge and also due to this charge. So we shall substitute and get the output, which is 0. Therefore, the work done from D to E is equal to the charge being transferred times the potential difference, which will be that, and then you get the answer which is needed. So work done from point to point, you will use potential difference. Work done from infinity to a point, we use electric potential. Then question 6 came from UNEB 2018, paper 2, question 9c, and says, 2 point charges, this and this, are placed at points A and B as shown in the figure 4. So the charges A and B, there is this charge and this charge. Calculate, Roman 1, the electric potential at P. So at P due to this charge and also due to this charge. Then the work done in moving a charge of this from P to Q. So from one point to another, we have to get potential difference. So we also need the potential at this due to this and also due to this. Now the diagram may look a bit scaring, but the easiest way is to redraw it. So let's come and redraw the diagram. So we have point A, we have point Q, and we have point B. Then we also have point P. So the separations, what we have done, we have converted from centimeters to meters. For example, this was 90 centimeters, it is now 0.9 meter. 90 centimeters, it is now 0.9 meter. And this is 120 centimeters, it is now 1.2 meters. That's what you're seeing here. So now this one looks a little easier to work with. So you come and say, for you to get the electric potential at P due to this charge, you need this distance PA and this distance PB. So these distances are the same. Therefore we shall come and why are they the same? It is because this is an isosceles triangle. I think you realize that this line or perpendicular bisects this and this, meaning even this will be equal. Therefore PA and PB are the same, and they will be got by Pythagoras theory of any one of the triangle. If I use this, it will be this squared plus this squared, everything under square root, to come up with 1.5 meter. Therefore electric potential at P, it will be due to this charge and also due to this charge. So you substitute and get the output as that. What about, so that was electric potential at P, and that's what they wanted. Then Roman 2, they wanted work done in moving the charge of -3 microcoulomb from P to Q. That means we need electric potential difference. To get that potential difference, we have to get electric potential at Q first. So at Q, it is also due to this charge and also due to this charge. So substitute and get the output as that. So now that I've got the two electric potentials, I can get the work done, which is charge being transferred times the potential difference. Then I'll substitute and get the answer they wanted. So now shall start our topic, electric field intensity between two parallel conducting plates. So for you, we are going to derive a formula. Therefore, we shall start with the relationship between electric field intensity and electric potential. Now, both these terms are not weird to you. I believe you have covered electric field intensity E and also electric potential V. So now we are going to first get the relationship between these two terms. So here we shall consider two neighboring points A and B in the field of a point charge Q. So close together, note this word, close together, that the electric field intensity between them is constant. This condition is very vital and is equal to E as shown below. So shall make an illustration. So these are the 2 points so close together, meaning that there will be a small change in potential. Here it was V, here it is V plus small change in V. And also a small change in distance. Here it was X, and here it is X plus small change in X. And this is our electric field intensity. So if the potential at A is V and that at B is V plus small change in V, the potential difference between the 2 points A and B will be given by VAB, which is VA minus VB. So when I subtract, it will be V minus V plus small change in V. Then you realize that this and this can cancel. Then this and this gives you a negative, and this one is here. So we shall call that equation 1. So we shall now also come and say that work done to move a positive charge of 1 coulomb from A to B is also equal to PD and is given by VAB, which is potential difference equal to electric field intensity times the distance moved. So where is this formula coming from? First of all, we know that the formula we know about potential difference or potential is KQ over R. Then the formula we know about intensity is KQ over R squared. Okay, now if you look at these two formulae, it implies that if I want to get this one from this, I'll have to multiply by R. where r is the separation. But in this case, we're using distance as x, so it means that if I'm apply this, if this is x, and I'm applying by motion in x, I'll be able to get k2 over x. So that is where the relationship comes from. To get potential, you have to multiply intensity times the distance or the separation. Now when I equate the two, I'll come up with this. And when I make this the subject, I'll come up with this. Then in the limit, as motion in x tends to 0, this one tends to dv dx. And basically this is the relationship between intensity and potential. So dv dx is what we call the potential gradient, and it is the rate at which potential rises with distance. So basically this is the relationship we wanted, and now we can go ahead to get the formula of electric field intensity between two parallel conducting plates. So we shall consider two parallel conducting plates A and B at distance d apart, so separated by a distance d, and between which there is a potential difference V. So let's first illustrate that also. So there are two parallel plates A and B separated by a distance d. But they say there is a potential difference, meaning we have to connect it to the battery, where the potential difference is V. So because of this potential, there will be a charge. This will be charged now, positive and negative. And because they are now charged, there will be an electric field moving from positive plate to negative plate. So we are following the same rules. Electric intensity moves away from the positive charge but moves towards the positive charge. Then what you should realize is that these ones are straight, but towards the end they are a little curved. So when they tell you to draw an electric field between two parallel plates which are charged, always remember to make these ones towards the end a little curved. So this is what I've been talking about, that the field between the plates is uniform apart from the edges. Now from this expression which we have derived in the previous slide, it implies that potential difference at all points between A and B away from the edges are equal, thus a uniform field. And therefore E is equal to V over D. So in this case, the SI unit for electric field intensity will be volt per meter. This is volt and this is meter, so it will be volt per meter. Previously, we saw that E is equal to Newton per Coulomb because the formula was F over Q. F over Q. But now in this case, it will be volt per meter if I use this formula. There are three cases which you need to know. One is that if a charged particle is placed inside an electric field, it will be attracted towards a plate having a charge opposite to that of the particle. The electrostatic force of attraction acting on the particle is thus given by, so let's first see that. So if you look at this, for example, now this is positively charged and this is negatively charged. If I bring a negative charge here Here there will be like charges, so there will be repulsion, but here there will be attraction. So this charge will be moving in that direction, or the force will be in that direction. If I bring a positive charge, here between this there will be repulsion, but here attraction, so the charge will go in this direction. So what we are doing, we are following the law of electrostatics, where like charges repel and unlike charges attract. So the force will be given by F equal to E2. Remember we saw that E is equal to F over 2. So if I make F the subject, it will be E2, which is this. So that is case 1. Now we shall go to case 2. Case 2 says that if a charged particle is placed inside the field shown above in the diagram above and it remains stationary, it implies that the weight of the particle is equal to the electrostatic force acting on the particle. So for example, here in the diagram, for the particle to remain stationary, it should be negatively charged, such that it is repelled from the bottom. Therefore, here the electrostatic force will be in this direction towards the positive plate, and there will also be a weight. Weight always acts vertically downwards. So for it to remain stationary, it implies that this force is equal to this weight, which is mg. That means that F is equal to mg, and we already know that F is got from here, and m is the mass of the particle, g is the acceleration due to gravity. So that is case 2. What about case 3? Case 3 says, if a charged particle is moving inside the field and in the direction perpendicular to the field, the electrostatic force acting on the particle is also given by this. So we use Newton's second law that F is equal to ma. So m is the mass and a is the acceleration, and F is the electrostatic force, but should be the resultant. So resultant, what does the word resultant mean? Resultant means that, for example, if there is this force acting and there is this, so this F is this one, and there is this mg, and the particle moves upwards, it implies the resultant will be this minus mg. If it is moving downwards, then the resultant will be mg minus F. So that is Newton's second law. So you should know that this F is the resultant force. So what we should note is that the equations of motion can also be used to obtain the velocity of the moving charged particle. So equations of motion are those ones. The first one is V equal to U plus AT. Second one is S equal to UT plus a half AT squared. And third is V squared is equal to U squared plus 2AS. So with that, we can now start working out the questions. So question 1 came from UNEB 2016, paper 2, question 9b, Roman 3, and says, two metal plates A and B, 30 centimeters apart, are connected to a 5 kilovolt, note that word kilovolt, as shown below. When a small charged sphere S of mass 9 exponent negative 3 kilograms is placed between the plates, it remains stationary. Note this word, remains stationary. Indicate the forces acting on the sphere and determine the magnitude of the charge on the sphere. So here it means we have to draw a diagram of the sphere and show the forces acting on it. So like we said, for the sphere to remain stationary, it should be negatively charged. So this will be the weight acting downwards, and there will also be electrostatic force acting upwards. So those are the two forces acting on the sphere. But they also wanted the charge, so since the sphere is stationary, it implies that this force is equal to this weight. Therefore, I'll come and substitute for force. We already saw in case 1 that F is equal to e.t.c and weight is equal to mg in case 2. When I equate the two, I'll also remember that electric field intensity is equal to V over D. We have already seen that. Therefore, I can make Q the subject by taking all these ones this side to come up with this. Now, next is to substitute. Substitute for M, which is the mass, G, which is acceleration due to gravity, and D, which is the separation of the plates. Then V, which is the potential difference. It was in kilovolts, that's why it is multiplied by 10 to the power 3. Then I'll get the answer, and that will be the charge they want. It will be the magnitude of the charge they want. So that was question 1. Now we shall go to question 2, which came from UNEB 2014, paper 2, question 8D. It says, a charged polystyrene sphere of mass 2 grams, not this word grams, so it means it has to be converted to kilograms, is suspended by a fine nylon thread between 2 plates 5 centimeters apart as shown below. So it's the diagram. When a PD of 2 kilovolts is applied across the plates, the thread attached to the sphere deflects through 30 degrees. Calculate the charge on the sphere. So that means that it was attracted in this direction for it to go towards the side. So to calculate the charge on the sphere, we shall have to first redraw and then show the forces acting on that sphere. So we shall redraw the sphere and show the forces acting on it. Okay, of course the first force will be the weight. It has to act vertically downwards. I think we realize we're writing 0.002 G. Now this G is no longer grams. This G is acceleration due to gravity. We are writing mg, where m is the mass in kilograms. So the 2 grams must be converted to kilograms. Then another force will be the attraction towards this plate of 0 volt. This is the electrostatic force. Then another one will be the tension in the string. So those are the 3 forces acting. Therefore, we shall come and say that resolving vertically, this vertical component of this is upwards, and this one is downwards. So it will be this equal to this. The vertical component is t cos 30. Why? It is because the angle is lying on the vertical. So when I substitute, I'll be able to get the value of t as that. Then I'll come and resolve horizontally. Horizontally, it will be t sine 30 equal to f. Then I substitute for t to get the value of f as this. But I know that f is equal to e.t.c, therefore, and e is equal to v over d. Therefore, I can come and choose the subject to come up with this, then substitute for f, for separation, and for potential difference. Then using a calculator, I can get this answer, and that will be the answer they wanted. Then question 3 came from UNEB 2020 paper 2 question 9D and says figure 4 shows 2 parallel metal plates placed 10 meters apart in a vacuum. with a potential difference of 100 volt between them. A point charge of positive 2 microcoulomb is transferred from A to C following the path shown. So this is the path they are meaning from A to B and from B to C. So the question is, if AB is parallel to the metal plate, if this one is parallel to this, and BC is 10 meters long, BC is 10 meters long, which is here, find the work done in moving the point charge from Roman 1 from A to B and explain your answer, and Roman 2 from B to C. So I think you remember under electric potential, we cover that part of work done. And work done will be potential difference times the charge being moved. And the charge being moved is this one. So the first thing to do is to get the potential difference. So let's start with Roman 1. So electric potential at A will be given by this. Now where is this coming from? Where is it coming from? We know that from here up to here the potential difference is 100. But this is midway. If you look at this, this is half of this. Therefore the potential difference must be half. And to get that half, we have to say this distance over this times this potential difference. That's how we get the 50. So in other words, it is shared, like we said, in between the plates the electric field is uniform, meaning it is equally distributed. Therefore from here to here, the fraction is 5 over the total, which is 10. Of what? Of this total potential difference. Therefore, we shall come here and say that is why you see here we are saying potential at A is 5 over 10 times 100, which is 50. And the same applies to B because they said it is parallel, meaning that the distance from here to here is the same distance from here up to here, which is 5. So both are at a potential of 50 volts. Therefore, work done will be charge times potential difference, which will be 0 joules. So in other words, there is no work done. Why is it so? So we shall give a reason that there is no change in electric potential from A to B. So it is 0 because the potential difference is 0. And that's what they wanted. Then Roman 2, they wanted work done in moving from B to C. So we already got the potential at B, meaning we have to get the potential at C in order to get the work done. So to get the potential at C, we have to get this distance. We have to get the distance from this plate, up to point C. Now how do we get it? If I draw this dotted line, I'll be able to get from here up to here. And from here to here, this is 60 and this is 10, meaning from here to here it will be 10 cos 60. We are resolving. Now 10 cos 60 plus this 5 will give you the distance from here up to here. So let's first do that. So we shall come here and say that electric potential at C is equal to the fraction, so the distance was 5 plus 10 cos 60 over the total distance, which is 10 multiplied by 100. You'll be able to get 100 volt. Therefore, I can now get the work done from charge times potential difference, and to be this, and that's what they wanted. Then question 4 came from UNEB 1994, Paper 2, question 8e, and it says, a particle of charge positive 4 exponent negative 9 Coulomb is situated between two parallel plates, across which a DC potential difference is applied. When the particle is moved 6 centimeters against the electric field, this work done, 8 exponent negative 5 joules of energy is used, and kinetic energy of the particle changes by this. Calculate Roman 1 the work done by the electric field, and Roman 2 the magnitude of the electric field. So we shall start by Roman 1. So for Roman 1, we already know that we shall say that change in kinetic energy is equal to work done in moving the charge minus work done by the electric field. Remember, we said the particle is moved against the electric field, meaning that the electric field is opposing the motion of the particle. That is why you have to first subtract it off, because it opposed the motion. Therefore, when I substitute, change in kinetic energy is that, work done is that, and work done by the field is what we want. So make it the subject, it will be this, and that's what they wanted. Then for Roman 2, they wanted magnitude of the electric field. So we know that work done is equal to charge times potential difference. Therefore, work done is that, charge is that, potential difference we don't know. So we can make it the subject to get this as the potential difference. Therefore, electric field intensity is equal to V over D. V is here and D was given the question. You'll be able to get your electric field intensity. And that's what they wanted. Then question 5 came from UNEB 1999, paper 2, question 10C, and says two large oppositely charged plates are fixed 1 centimeter apart as shown in the figure below. The PD between the plates is 50 volt. This is what is here. An electron enters the region between the plates at an angle of 45 degrees, as you can see here. As shown, find the maximum speed of the electron must have in order for them to strike the upper plate, in order to hit this upper plate. So that the mass of the electron is 9.11 exponent negative 31 kilograms. So here we have to also redraw the diagram. So we shall first redraw the diagram so we can show the motion, the full motion of the electron. Okay, so I think we can see that it has struck the upper plate, and that's the condition they wanted. So we shall start by saying that from Newton's second law, F is equal to ma, and force is equal to electric field intensity times the charge. So we are not writing Q because it is already known that the charge of an electron is denoted by E. Therefore, electric field intensity expanded to give you V over D. Then make A the subject, so this will be the acceleration. I'll come and substitute in order to get the acceleration. Substitute for this, it is a constant. It will be available in the paper you'll be doing. Then this is the potential difference, and this is the separation to meters. To convert it to meters, this is the mass which was given in the question. So in the end, you'll come up with this as the acceleration of the electrons. Now, using the third equation of motion, remember we said equations of motion can also be used. So when I use the third equation of motion, I'll consider vertical motion. Vertical motion. That is why we are saying y to mean, this means vertical component of velocity, vertical component of initial velocity. So I'll come and substitute. The vertical component at this point is 0 because this is the maximum point. I think you remember that under projectile motion of physics paper 1 in mechanics. So this vertical component is 0 at maximum point. Then this one is the initial vertical component we have to resolve. So velocity here is u. When I resolve, it will be u sine 45. It is squared, so don't forget the square. Then 2 times acceleration. Now we no longer use acceleration due to gravity, we use the one we have got. Then times the displacement. Now, why are we writing 0.5? It is because from here to here, vertically it is 1 centimeter, meaning from here to here it will be 0.5 centimeters. But we have to convert to meters. That is why you are writing 0.5 exponent negative 2 to give you the displacement in meters vertically. Now here, the good thing, we have only one unknown, so we have to simplify and get that unknown, which will be this. And if you look at the question, that is the velocity, the speed they wanted. They only wanted speed. That is why we are not getting, okay, the direction was given. So they wanted speed means only magnitude. So we can't state the direction here because speed means magnitude. So that has been electric field intensity between two parallel conducting plates. But remember, we said we are going to cover two parts, so we shall also cover the closest distance of approach of an alpha particle to the nucleus. So an alpha particle directed onto the nucleus is deflected through a large angle, and the smallest distance alpha particles can reach, note this word, smallest distance, can reach the nucleus is referred to as the closest distance of approach of the alpha particles to the nucleus. So we need to illustrate this. So we shall suppose an alpha particle of mass m moving with an initial velocity v collides head-on with an atom of atomic number z. The particle is deflected as shown below. So we shall try to illustrate that. So this will be the atom and this is the nucleus. So an alpha particle will come and collide with this atom, but cannot reach this nucleus, so it will be repelled along the way to go back in the path it came from. Now this distance between the nucleus and this part where the particle turned, alpha particle turned, is what we call the closest distance of approach, and that's what we have denoted as R naught. So basically this is what we are looking for in this part. So we have to derive how to get that closest distance. So what happened is that the alpha particle will be slowed down until it comes to rest at a distance R naught from the nucleus and then repelled back. I think we have seen that. So R naught is the closest distance of approach, and that's what we want. Therefore, at R naught, the kinetic energy of the alpha particle is converted to potential energy of the nucleus alpha particle system. This implies that if E is the magnitude of the electronic charge, the charge of the alpha particle will then be 2 times E. Then the charge of the nucleus will be Z times E. So this Z is the atomic number, we saw that, times the E. Now someone may ask, where is this 2 coming from? It is because the alpha particle in your physics 1, it was 4, 2, meaning that it has an atomic number of 2. This one, the nucleus, in the question we said the atomic number is Z, so it will be atomic number times the electronic charge. Atomic number times the electronic charge. So that is where the 2 is coming from. So here we say that they are equal, so it is converted, meaning that at this point, initial kinetic energy of the alpha particle in joules is equal to potential energy of the nucleus alpha particle system at the distance of closest approach. Therefore, if we substitute, kinetic energy is given by 1/2 mv squared, that we already know. Then potential energy will be, remember potential energy means there are 2 charges, that's why you see at Q1, Q2 over 4 pi epsilon naught R naught. We saw this formula under electric potential. So these 2 will be equal, and when I make this the subject, if I'm given the rest, I can make this the subject, and that will be the closest distance of approach. So basically this is the formula we're going to be using in this part. So question 1 came from UNEB 2020 paper 2 question 9e, and it says an alpha particle of charge this and mass this travels with a velocity v directly towards the nitrogen nucleus, which has a charge of this. The alpha particle reverses direction at a distance this. So this will be the distance of closest approach from the nitrogen nucleus. Roman 1. Explain why the alpha particle reverses direction. And Roman 2. Find the initial velocity v of the alpha particle. So let's start with Roman 1. So Roman 1, we shall say that the alpha particle loses kinetic energy as it approaches the nitrogen nucleons. I think we already saw that. And this is transferred to electrostatic potential energy. Therefore, at some point, all, not this word, all, the kinetic energy of the alpha particle is lost and it is repelled back by the nitrogen nucleons. So that is one way of explaining, but alternatively you can also say that the repulsion between the charges retards the motion of the alpha particle, and as a result, at some point the velocity of the particle is below 0, meaning it is now negative. Thus, the repulsion causes the particle to reverse its direction. So any of the 2 is okay. Now we shall go to Roman 2. So we shall remember that on closest approach, all the kinetic energy of the alpha particle is converted into electrostatic energy of the alpha particle nitrogen nucleus system. Therefore, we shall quote the formula, which you already know, and then now we are not using 4 pi epsilon naught, because we said we already know by now that K means 1 over 4 pi epsilon naught. So we shall come and substitute. Half is there, mass is there, V is what they want, K is this, Q1 is that, Q2 is that, and separation is that. That means that my aim is to make V the subject, and V will be equal to this, and that's what they wanted. Then question 2 came from UNEB 1999 paper 2 question 9c, and says alpha particles with charge this, each having kinetic energy this, are incident head-on gold leaf nuclei of this in a gold foil. Calculate the distance of closest approach of an alpha particle to the gold nucleus, and they give you that E is equal to that. So E is a constant and will always be given. So on closest approach, we already know that all the kinetic energy of the alpha particle is converted into electrostatic energy of the alpha particle gold nucleus system. That means that these two are equal. Therefore, we shall quote the formula. Now, this one was already given. Then the potential energy is K1 Q2 over R, which is the separation or closest distance. Therefore, come and substitute. And you know this is that, and this is that according to the question. And this is the closest distance of approach. Therefore, when I make R not the subject, this K is already known, 9 exponent 9. Then this 2E times this gives you 2 times 79, which is 158. Then E times E, which is E squared. Then this one comes down. But I already know the value of E, so I can substitute for E, and I'll be able to get my R naught as this. And that's what they wanted. So that brings us to the end of this video. Thank you for watching, and be reminded the next video will be on capacitance of a parallel plate capacitor. So if you have not yet subscribed, please click on the subscribe button below this video so that you can receive updates when the next video has been uploaded. And also, if you know of any student who is not yet on this platform, please share the link of this video via social media platforms like Facebook and WhatsApp so that you can all benefit as a family.